So I am completely delighted to be able to tell you about our magnificent universe, my favorite thing. And I want to tell you about our quest to try and understand this bigger thing that we're a part of. And the reason that I find it so compelling is that it's our home. We are here on Earth, but we're part of something much bigger. And the stuff it's out there is part of our home too. And it's also our story. If we think about how we on Earth came to be here, we came to be here through this long process, this bigger process that's embedded in the story of our universe. So those two things bring it into our home here. And so I'm a professional astronomer. I try and ask questions about the universe. Those are the questions that I find most compelling. It's what's drawn me to study the universe. And the kind of questions I have, and the questions that I talk about also in my new book, are these. I want to know, what is space? And what is our place in it, our place here on Earth? I'd like to know if there's life elsewhere, which is such an exciting question that we're making huge progress on. I'd like to know if the universe had a beginning and what that even means. And I'd like to know what, if anything, lies beyond our laws of physics, the things we understand already. And so as an astronomer, we have to kind of pick the thing that we're going to spend our time particularly researching. And my area that I particularly research is cosmology. And cosmology is the area of astronomy in which we answer questions about the whole universe on average. We don't worry so much about the details, and we ask questions like, how old is it? And what is it made of on the whole? And is it growing? And what's going to happen to it in the future? And this is my telescope, my team's telescope, the Atacama Cosmology Telescope. It's one of the highest in the world. It's in the northern deserts of Chile, in the Atacama Desert, and it's 5,000 meters up in the air. And we use it to stare as far out into space and back in time as we possibly can. And I use it to try and understand the origins of the universe. But we're going to start a little closer than the most distant parts of the universe and a bit closer to home, because I want to start by taking you out through our home, our universe, from the place that we're most familiar with, out to the far reaches, out to the far edges. So our home in the universe, the thing that we are most familiar with, the thing that we know we're a part of, is the solar system. That's the thing that we learn about first, and we know we've got our 8 planets, used to be 9, 8 planets, and a whole bunch of rocks orbiting around our wonderful sun, the source of our heat and light. And one thing I find astonishing about our solar system is actually how big and very empty it is. If you were to imagine fitting the solar system into this hall, into this room, and you imagine Neptune, for example, the stuff beyond Neptune, but let's imagine Neptune circling round this room, round the edge, then the sun in the middle of this room would just be the size of a peppercorn, just a couple of millimeters across. And the Earth, which is 100 times smaller, would just be a speck of dust. And the rest of that whole space, the thing that we think of as kind of jam-packed full of planets, is actually completely empty. These things are tiny. And the solar system itself is pretty big, although we're going to go bigger. Out to Neptune is about 3 billion miles. But these numbers start to become a little bit intangible. And what we like as astronomers to make things manageable. Space is really big, and it can kind of overwhelm you if you don't come up with ways of trying to handle them. And so one thing we use a lot of is using a measurement of distance that is how far light can travel in a given time. So light is the fastest thing we know of. It travels at this incredible pace, and 200,000 miles a second. And we think of how long light takes to reach places. And so it takes about 5 hours from light to get from Neptune into us. And that's compared, for example, the moon, our closest neighbor, light takes about a second to reach us from there. So Neptune really is pretty far away. So it's kind of phenomenal that we can send out probes through the solar system to go and visit these places. And we've known actually how big the solar system is since the 1760s, when there were these marvelous expeditions. I would say the first big international astronomy collaboration took place when teams of astronomers from around the world went on these phenomenal expeditions to different locations around Earth to go and observe the transit of Venus across the sun. And by observing it from different locations on the Earth, they were able to judge how far away Venus is by watching the different path of the planet across the sun's face. And they got the measurement really remarkably well, about 100 million miles from us to the sun. And that set the scale of the solar system. Now, I said we can go and send probes out into the solar system, but that's as far really as we can go. There are wonderful ideas about going out to the stars, but really, they're really far away. It's realistically, we're going to have to only sit here on Earth and look if we want to go out further. So the nearest stars to us, our very nearest neighbor, is Proxima Centauri, and its light takes 4 years to reach us. 4 whole years since the light set off and reaching our eyes. Most of the stars, the beautiful stars that you see above us, are tens of years, hundreds of years, thousands of years that light takes to reach us. And if you think about the Orion constellation, the beautiful Orion's, the stars in Orion's belt, the light from those set off 1,000 years and have been traveling for 1,000 years, and just now you see them in the sky. And so we have this sort of cocoon of stars around us, but they are this incredible distance away. And now we've known about how far those are away since the 1800s. And the way we kind of figure out where they are uses this neat method of parallax, which we're going to actually all try right now. So let's say I wanted to measure the length of my arm, but I couldn't be bothered to measure it actually with a ruler, okay? So there's a different way you can do it. You can use a thing called parallax, which is you hold out your arm in front of you, and let's all do that now. Oh, yeah, good. And I want to measure the distance to my finger. Now, close one eye and see where your finger is compared to the wall behind or the people behind you, okay? And now close the other eye. You should see it move. Yeah, good. Now bring your arm closer to your face, as if you had a really short arm. And now do it again. Moves further? Good, okay. That's parallax. So here, it moves, the further it moves, the closer it is to you. And if I know the distance between my 2 eyes, a few centimeters, and I know the angle that my finger moves, then I can use simple right-angle triangle trigonometry that many people have learned in school to figure out the length of my arm, maybe 60 centimeters. And that's all very well, not so useful for the length of my arm, but really useful for stars, because I can't get to a star. But what I can do is I can do parallax. So for stars, the length of my arm now becomes the distance to a distant star. And my 2 eyes now become the Earth, 6 months apart. So what you do is you sit on Earth and you look at a star against a backdrop of more distant stars. And then you wait 6 months for the Earth to go around the sun halfway around. And you look at it again from the other eye. And you see what angle it moves through. And the bigger an angle it moves through, the closer it is to you. And so now the distance between your 2 eyes becomes twice the distance of the Earth to the sun, about 200 million miles. And so it's a really pretty ginormous triangle. We love triangles in astronomy. We love enormous triangles. So this gave the first measurement to the stars, back in the 1800s. And this told us how far away they are. Now, the stars around us are actually just part of something bigger. We're going to keep going out until we get to the edges. Our little group of stars around us are just part of a much vaster thing, which is a wonderful galaxy that we live in, the Milky Way galaxy. And that's a collection of about 100 billion stars, that are all gathered together by the force of gravity of those stars, pulling them together into this wonderful swirling disk. And sometimes when we're lucky here on Earth, we actually get to see it. And this is an image up here of how we would see the disk of the Milky Way galaxy in the night sky. Now, from London, you don't get to see that. And I've only seen it a few times. And it's phenomenal. So I urge you, if you have ever a chance to go to a really dark sky, please go, because it is incredible. And so what is this? We're living in this big disk, this disk of a galaxy. And why do we see that strip of light across the sky? This is where this mysterious saucepan lid comes in handy. Okay. So imagine what we think we have is we have this disk, a swirling disk of stars. And we're living in it, and we think we're living in it about halfway from the middle to the edge in our little group of local stars. And because we're kind of embedded in the disk, if I'm in the disk like this, and I look straight through the thick disk of stars, then I'll see a band of light exactly where that disk is. But if I look out either side, I see very little. There aren't very many stars in those directions. Or conversely, if I looked across that direction, I'd see a band of light too. So this band of light that you can see in the sky that we call the Milky Way, and it's called the Milky Way because it looks like Milky Way, is just us seeing, being inside the disk of stars and seeing a bright light where you see that edge bit. But how do we know? So this, and it's big enough, so we think now we have pretty good measurements, that the size of this disk of stars that we live in is about 100,000 light years from side to side. So if you set light off on a journey, it would take 100,000 years to get from one side of our galaxy to the other. And so let's just remember, so if our group of stars around us were just the ones like tens of light years away from us, then we would be like, again, a little peppercorn like bobbing around the galaxy as it spins around. And the whole thing spins around every 200 million years or so, this giant sort of gradually rotating disk. But then we might ask the question, well, how do we know even the extent of our Milky Way? Because again, all we get to do as astronomers is we sit here on Earth and we look. And that's all very well, but inferring where things are when all you can see is this kind of two-dimensional surface around you can get quite challenging. And the key to this came from this fantastic astronomer, Henrietta Swan-Leavitt, who I would say is not nearly famous enough because she did this awesome thing. She was an astronomer working at the turn of the last century in the States. She was working at Harvard College Observatory, and she started working there in the late 1890s. And she was part of this amazing group of women astronomers known as the Harvard Computers, who were hired by another astronomer, Edward Pickering, to analyze photographic images of stars that were taken by their male colleagues, because as a woman at that time, you weren't allowed to use a telescope, God forbid. And he gathered this group of women to study plates after plates, photograph plates of images of stars, to classify them, to measure their brightnesses, to measure their colors. And it was really hard work, and they weren't really allowed to do what they wanted. They were just kind of set to work. They weren't paid very much, but they turned out to be really quite good at it. And she discovered this amazing property, which is there were the stars that vary their brightness with time. So most stars kind of are constant, just twinkle in the sky and their brightness is constant. But some of them vary. And there's this particular class of stars called Cepheid variables, which actually pulsate over time. They grow and shrink, and as they grow and shrink, they change their brightness. And she discovered this pattern about these stars, which was that the longer they took to pulsate, the brighter they were intrinsically. And so a star that took weeks or months to pulsate was much brighter than one that took just days. And this actually proved to be the key to unlocking the whole scale of our galaxy and actually our universe as well. Because there's this key thing. If there's this relationship between the time a star takes to pulse and how intrinsically bright it is, then you can figure out how far away it is from you. Because the problem usually in astronomy is that if all stars were the same brightness as each other intrinsically, if everything was like a 100-watt light bulb, then you could figure out where things were in space just by saying how bright did they look. You know, a standard 100-watt light bulb, if it's closer to you, it looks bright. If it's further away, it looks dimmer. But if you don't know how bright it was to begin with, you can't tell where it is. But these things, these Cepheid stars, if you could only measure their timing of how quickly they pulsed, which is a relatively easy measurement to do, you then know intrinsically how bright they are. And then you measure how bright they seem, and you can figure out where they are. And so Swan Leavitt made this discovery in 1908, and then really quickly, astronomers took this law, it's now called Leavitt's law, and figured out how big the Milky Way galaxy is. This is an artist's impression of what we think it looks like. We'll never be able to take our own picture of it because we can never get outside it. It's just much too big. There's no way we could ever climb out. So we think it's these swirling arms of stars swirling in. And the darker bits are where we think we have sort of debris. We call it dust, cosmic dust grains that's intermixed with the stars, and also gas, swirling in these spiral arms to a more central region of brighter light. And so that's our Milky Way galaxy. Now, until 100 years ago, astronomers thought that was it. That was our entire universe. That was the edge, nothing beyond it. And actually, it was this measurement, this discovery of Leavitt, of this relationship, that allowed this guy, Edwin Hubble, to figure out that there was actually something beyond. Because 100 years ago, there were these astronomers had seen that in the sky, they had the stars of the Milky Way, but there were also these smudges of light that no one really knew what they were. They were called nebulae, clouds, basically, of light. And they weren't identified. And then Edwin Hubble, it's hard to find a picture of him without a pipe. I think he was working at the Mount Wilson Observatory in California, doing incredibly hard. Back then, telescopes were much harder work than they are now because you would have to track stars kind of all night on the telescope, following them with your telescope. Now it's all automated and the telescope kind of follows something for you. But back then, you had to kind of painstakingly track a star. Anyway, he looked at these smudges of light and he realized that there were some of these magic Cepheid variable stars in those smudges of light, pulsating. And he used the fact that he knew then, if he could measure how quickly they pulsated to figure out how bright they were, he realized that they were far, far, far too dim. They couldn't possibly be in our galaxy. They had to be much further away. So if, for example, if as we figured out that the galaxy is 100,000 light years across, these were millions of light years away, much, much further. And so this was this huge opening up of our horizons that he demonstrated that there are indeed these other galaxies far beyond our own. And we can now, he wouldn't have been able to take these pictures at the time, but now we have these magnificent images of actual galaxies that are different from ours. And so this is a real picture of a galaxy far, far away. And again, you can see that this beautiful spiral disk that it would be the shape of a disk, right? We're seeing it like that, right? With most of the stars in the middle and these arms of stars spiraling into the center. And so if we now look out, again, these are maybe millions of light years away from us, or then even further. They're what we step out and we see the kind of building blocks of the universe. And these things tend to clump together a little bit. So if we have a bunch of galaxies, they tend to like to group together, kind of in small groupings, a bit like cosmic towns or cities with hundreds, thousands of galaxies together. And so this is a nice example of a galaxy cluster. um, taken by the Hubble Space Telescope, named after Edwin Hubble. And here what you're seeing is a grouping together of galaxies, where every one of those spots of light is an entire galaxy, each of those with perhaps 100 billion stars. And this is one of the largest objects in the universe, a galaxy cluster. And I think it's extraordinary. And so you might have, hundreds to thousands of galaxies all drawn together. And so we're now on scales of hundreds of millions of light years, these giant objects in our universe. And then if we look out further still, we find more of these. We find our universe full of galaxies grouped together into these clusters of galaxies. And in fact, there's an even one level still up, which is maybe unimaginatively called a supercluster, which is where, again, local gravity kind of draws some of these big clusters together into a grouping. And so we live in one of those too. We live we don't actually live in a big galaxy cluster. We live in a small group, the local group, which is only 3 big galaxies and some little ones as well. We're in a small town. But we're pulled together with other clusters of galaxies around us. And we thought for a while we were part of the Virgo supercluster. But then quite recently, some astronomers said, actually, there's more that's being kind of pulled gravitationally by gravity towards us, which is the larger supercluster called Laniakea. We're not quite sure which we're part of. It might be Virgo, it might be Laniakea. It's quite hard to tell because gravity is kind of pulling stuff in, but other things, which I'll come to later, are pushing stuff away. But then we've stepped out really we can step out now to the edges of the observable universe. So if we look out any direction in the sky, if we try and look in a gap in the sky, don't look at a star, we just see galaxies as far as we can see. So this is just a snapshot from the Hubble Space Telescope of a tiny piece of sky where every one of those spots of light is a galaxy. And so we can see out to this incredible distance, but it is actually a finite distance. So there is this thing that we call the observable universe. And it's a funny concept because the idea is that there is actually only a finite part of space that we can actually access. And that's because we actually think that the universe has a finite age. It hasn't been around forever, and we'll get to that. But the fact that it has a finite age, which is now we think is about 14 billion years old, means that there's an edge to what we can see. We can only see things now on Earth that light has had time to travel from since the beginning of time. So anything that's so far away that in 14 billion years light couldn't have reached us, it's beyond our horizon. It's beyond, and we call it a cosmic horizon. It's beyond our horizon, and it's outside what we call our observable universe. So we have this sphere centered on ourselves, with us at the middle of it, which is the observable universe. And that doesn't mean that we're at the middle of the universe, right? It's very important. We're just at the middle of the part we can see. And the distance of that edge, the size of that, you might have thought that the size of that, the distance to the edge of that, would be 14 billion light years. It turns out to be actually further, about 3 times further, because space has actually been growing during that time, which we'll come back to. It's about nearly 50 billion light years to the edge of the observable universe. And there's this kind of remarkable aspect of doing astronomy and looking out that far, which is that it's kind of like this time machine aspect of astronomy, which is that the further you look out into space, the further you see back in time. So we sit here at the middle of our observable universe, and we look out through increasing, the further we look out, the further back we're seeing. So the part of the universe we can see nearby us, we're seeing quite recently, as it was quite recently. But the more distant bits we're seeing as they were quite a long time ago. And the most distant parts we're seeing as they were billions of years ago. So it's a bit confusing, but very useful, because we kind of think that everywhere in the universe has evolved kind of the same. So if we could see like the very far away right now, we think that it's doing the same as we are, more or less, but we see it as it was in the past. And it's frustrating because we can't see how the whole universe looks like today. We just can't do that. But it's really useful because we get to see how different parts of it were in the past. And so by seeing how different parts of it were in the past, we can kind of piece together how we have come to be here now, because we can see things as they were. It's a bit like if you were to be an alien coming from a different planet and you wanted to understand how humans have grown, then if you give them a room full of 80-year-olds, they might be able to figure out like what humans look like, but they wouldn't have a good sense of how they were to evolve. But if you gave them a room full of a whole diverse range of people, if you gave them some babies and some kids and some grown-ups and some older people, then you would actually be able to reconstruct much better how humans evolve and grow. So actually, this idea that we can get to look at distant parts of space as they were a long time ago is really useful for us. We can kind of build our picture. Okay, so this is the kind of the tour of like the things that we can account for most easily in the universe. But soon we should be driven to ask a question of, this is not the universe. Well, it is in the universe. We should ask the question, which is the stuff that we're seeing, these galaxies, is that all there is? Because if we look at this picture, this is an image of the United States, what you see there, and if you were an astronaut flying high in the sky, looking down on Earth at night, what you would see of the Earth is the bright lights. You would see where there's people living, where there are cities and towns. What you wouldn't see is the darkness of the land underneath, where there's no significant amounts of light. And so the question should surely come, well, I'm looking out into space, and I'm only seeing the bright lights. What else is there? And it turns out that there's quite a lot. And it's been 50 years since actually we've had some idea that there's more to the universe than meets the eye. And a big part of this discovery came from this great astronomer, Vera Rubin, who is pictured here looking at an observation of using this thing called a spectrograph to look at galaxies. She's an amazing astronomer. She sadly died a couple of years ago, but she made this great discovery about the contents of our universe. So she's kind of an interesting character. She was a great leader of both astronomy, but also a promoter of women in astronomy. She had a pretty hard time starting out because challenging time. She did her degree in physics or astronomy and wanted to go and do graduate work. And so she applied to do a PhD at my current university, Princeton University, in the late 1940s, but she wasn't accepted because she was a woman, and they didn't take women at the time. So undeterred, she went to Cornell and successfully studied there. But then she moved to follow her husband to Washington, to Georgetown, and she had to complete her studies while looking after their young children. So she would go to lectures at night after looking after her young kids during the day. But nonetheless, that was fine. And she then, her big project that she wanted to work on was to look at the motion of galaxies, to understand how they move. And she realized that to look at them in great detail, she would need to be able to use a big enough telescope to observe the fine details within distant galaxies. And to do that, you need a telescope with a really big mirror. The bigger mirror you have, the higher resolution you can see. And at the time, the best one available was at the the Palomar Observatory in California. And so in 1965, she applied to use it, but they said, no, only men can use the telescope. But she persisted. And one of the reasons she was given was that there were no facilities, no bathrooms, women. She's like, this is ridiculous. And so she cut out a triangle of paper, a skirt, and pasted it on one of the men's bathroom doors. It's like, have a bathroom. So she was the first woman to ever use this magnificent telescope, this 5-meter telescope. And she worked with a colleague, Kent Ford, to build this spectrograph. What does that mean? It means they were looking at light from galaxies, but they were breaking it up into the rainbow of different colors, from red to purple, to look at the light in different wavelengths. They wanted to see how fast galaxies were spinning, and in particular, how fast stars were moving around in the galaxy. And you can do that. So let's imagine, again, this is my galaxy. It's spinning around. And I want to see the stars on one side, if you see it edge on, will be moving towards you, and the stars the other side moving away. And if you want to know how fast it's spinning around, then you can go and use the Doppler effect, which you've probably come across with a siren from a police car, for example. If something's moving away from you, the signal coming from it, be it sound or light, has its wavelength lengthened as it moves away from you. So the signal, the pulse rate, or the length, the distance between the peaks of a signal, the wavelength, increases as something moves away. So for sound, that lowers the pitch. That's what you hear when a police car goes past you. You hear it lower pitch. And with light, that lengthens the wavelength, and it shifts the color more towards the red end of the rainbow, which has a longer wavelength than blue or purple. And conversely, if something's moving towards you, it squeezes the wavelength shorter and moves it more to the blue or purple end. So with a spectrograph, you can break the light up from a galaxy into its different colors, and you can figure out how fast it's moving around. Now, why is that interesting? Well, the speed at which something moves around is just connected to how much gravity there is in the thing, how much mass there is. So, for example, the reason why we orbit the sun is because it's got mass. And if we made it more massive, we'd orbit it quicker. So the heavier something is, the faster something orbits. So she went to look at all these galaxies, and she measured very carefully how fast the stars in them were rotating. And what she found was incredibly surprising, she and Kent Ford. And she found that they were rotating much too fast. And particularly the ones at the edge of the galaxy, sort of out here, they were really going much too fast. And the only way that you could make sense of it going that fast was if there was actually some extra mass in the galaxy that you couldn't see. And it looked as if actually the galaxy was actually many times bigger than the visible disk of light was showing up, and with maybe 10 times as much mass as you could see from the stars. And so the picture of a galaxy turned into something that looks a bit like this, where in the middle of there is a tiny little blue disk of the visible stuff, that beautiful swirling disk of stars that we sort of maybe thought was the whole galaxy. And what Rubin's work showed was that actually it seems to be surrounded by an enormous sphere or halo of completely invisible matter, whose effect it is to make it all spin around faster, but is completely invisible. And Rubin actually realized that this idea had been brought up 30 years before by this astronomer called Fritz Zwicky, who was notoriously combative but very clever astronomer working in California. And he had looked at this cluster of galaxies, and he'd also seen this behavior of galaxies inside the cluster moving too fast around. And he'd actually written a paper about it in German, bringing up the idea that maybe there was invisible matter. And he called it in German Dunkelmaterie, which translates to dark matter. And so Rubin made the connection that this is what Zwicky had seen, and now she and Kent Ford were seeing it in all of the galaxies they were looking at. Many, many galaxies, same thing. And this became established, that there is invisible matter surrounding all our galaxies. It's not just surrounding our galaxies, it's in them, it's in here, it's in this room right now. And it seems that there's about 5 times as much of it as there is the stuff that we're made of. And we have no idea what it is. It's quite worrying. We kind of hope, and I would say that this happened, 50 years ago now, But the understanding of it, of where it is and how it's behaving, has just advanced significantly since then. And we're now just even more convinced that it's there, and perhaps even less sure about what it is. We'd hope that it might be a new particle, a particle that gravity acts on, but it doesn't really interact with stuff much at all. So a particle of it would fly through your body without stopping. And again, probably some of it is right now. Don't worry, though. But we hope that it was something that we kind of call a weakly interacting particle, which means it doesn't interact much, but it interacts just a bit, just enough that we could find it in a detector. And there were great hopes that we could actually create some of these particles at the Large Hadron Collider in CERN. But we haven't. And it's possible that we still might, but it hasn't happened yet. So some of our kind of most favorite ideas about what it could be have not shown up to be true. So now it's one of our outstanding mysteries. It's there, but we don't know what it is. So maybe one of you can figure it out. So we I'm doing a sort of, there's the visible parts of the universe, and this is a big invisible part. But there's another invisible part that's very exciting, which is planets. Until 30 years ago, we didn't know if there were any planets around the stars in the sky. Astronomers thought there probably were. It'd be kind of weird if we were the only solar system to have planets. But they're really hard to find because they're very dim. They don't give out much light, no visible light, just a bit of kind of warm infrared light. And they're very tiny. So they're mostly invisible to us. But we've recently, with better telescopes and better techniques, have managed to find them. So in the 1990s, the very first planet was found orbiting an entirely different star to ours, just the first one. And now, today, we've found thousands. And many of those have come from this wonderful satellite called the Kepler satellite. And what I'm showing you here is a still shot, and I encourage you afterwards to go and look it up online, of a selection of the solar systems that have been found around other stars out in the sky. Each one of those circles represents a whole solar system around a different star in the sky. And each of the dots on the circles is a planet. And they found them in this really neat way, which is that they were using transits of planets. If a planet passes in front of its host star, then it will slightly dim the light of the star while it passes. And then the star will go back to normal again once it's gone. And so Kepler managed to look for this very subtle dimming of light and has found thousands of planets this way. And using what they've seen so far, they assess that probably a good fraction of the stars in the sky have their own solar systems. And the most extraordinary diversity have been found. There are planets that orbit their sun in hours or days, orbit their star in hours or days compared to our 365 days. There are planets where there are the systems that orbit 2 stars at once, for example, or multiple stars. And one of the most exciting places that's going to be the subject of enormous future study is this place called TRAPPIST-1, which this is just an artist's impression of. We haven't taken these images yet, which is found by the Kepler satellite. It's a solar system with 7 rocky planets, only 40 light years from Earth. It's still quite far, but it's in terms of observing stuff, that's not that far. It's one of our nearest stars. And the planets, again, these are just an artist's impression of what they look like. We have not got these images yet. But they're there, and some of them are thought to have water on them, and it's an ideal target for future observations with telescopes coming up in the next 10 years. It's this incredible, and there are many coming. There are many coming that are designed to be able to study these in more detail and look for potential signatures of life. So this is a kind of whole invisible part of this bigger home we live in, which is all of these rich planets are going around the stars. And just because they're tiny doesn't mean they're not, of course, fascinating. We on Earth are much tinier than our sun, but I think we'd argue that we are probably more fascinating than our sun. Maybe, we're a bit biased. But it's, to me, that wealth of what we could find out quite soon, the next 10 years or so, about what's out there in terms of different planets is really exciting. So those are the things that are in our universe. But then we can come to thinking about the story that brought us here. And I'm going to focus on the big story, which is, are things changing in a big way at all? Because if we look out beyond, again, out into this bigger universe full of galaxies, has it always been there? And 100 years ago, this familiar guy on the left, Albert Einstein, was absolutely convinced that the universe was unchanging, that it is as it is, that nothing was changed. As it is now is as it always has been, that there could be no beginning, for example, and no end to the universe. But he clashed with this guy on the right, Georges Lemaitre, who was an astronomer and also a priest in Belgium, who argued against him and said, actually, I think the universe could be changing, and let's go and find out how. And actually, this guy on the right, Georges Lemaitre, the reason he thought that maybe the universe on a whole could be changing and could have a beginning actually arose from studying carefully Einstein's new theory of gravity, the theory of general relativity, which explained how space should behave. And the idea here is, if you sprinkle galaxies throughout space, they shouldn't just stay there, stay still. If you just sprinkle them and just plonk them down, then the gravity of all those galaxies should actually tend to want to pull things all back together again and actually shrink the universe down. Or if it's already growing through some means that we don't know yet, then it should still be moving outwards. And I want to demonstrate just quickly what we kind of mean when we talk about an expanding or a shrinking universe. And I'm going to use my universe here. This is a universe, by the way. This is a one-dimensional universe. I mean, imagine now that you're an ant living in a one-dimensional space, which is this piece of elastic. And I want you to imagine that you are living in one of these blue stickers, which is your one-dimensional, well, it's two-dimensional. Think of it as only living along this line. That's a galaxy. Each of these blue stickers are a galaxy or a marker in this ant space. And I'm going to model what I mean by a universe that grows in this space by simply stretching the elastic, stretching it apart. Okay? And a shrinking universe, I would bring it back down again. Grow it again, like this, shrink it back down. Now, what happens when I stretch a piece of elastic is it grows everywhere. It doesn't grow from one central place. The whole thing expands, or the whole thing shrinks. And so when we talk about an expanding space, is space growing? We're talking about something like this, where all of the galaxies in the universe sprinkled through it are moving apart from each other. And a shrinking space would be one where they were all moving together, like this. And that's very different from the idea of maybe something bursting out from a point in space. We think a space that grows is a space that grows everywhere. Now, this is just a one-dimensional universe. We think that we might be living in a universe that's like this in 3 dimensions, a bit like a stretchy elastic in 3 dimensions. And an analogy for that is a bread dough full of raisins. Imagine you take a small bread dough, fill it with raisins and yeast, and let it rise. The raisins will all move apart from each other in that dough universe. And that's kind of what we think of when we think of an expanding universe, is everything moving apart from everything else. So this guy, Georges Lemaitre, who was brilliant, but he made one error, which was that he wrote about his predictions and his interesting findings in a really obscure Belgian journal in French that none of the relevant people read. So he wrote this fantastic paper where he said, I think the universe is growing, and here's how we could go and figure out if it's growing. And, I have actually gone to figure it out. And, I think the universe is growing, and it started in a Big Bang. And huge news, really important results. No one read it. And it wasn't until 4 years later that it got translated into English and was read by the wider community. But he made this prediction that others did too, which is that in such a universe, okay, let's imagine, let's do this all together, right? Imagine I live in this, I'm back in this ant, and I'm in my stretchy universe. My universe is growing. And I want to know if I, as an ant living in one of those blue spot galaxies, how I can tell whether the universe is growing or not. And as an aside, I'll say that the reason that these are blue spots and not drawn on with blue pen is that we don't think in an expanding universe that a galaxy itself will expand. We think the gravity in that is too strong compared to how fast we now do think space is growing. So when we think about expanding space, anything inside a galaxy is not growing. So even if space is growing, like this room is not growing right now. Right? That's no, it's okay. So if you're an ant in one of these galaxies and you want to know if your space is growing, you can look out at galaxies around you, and they all should appear to move away from you if space is growing. If you picked any one of these galaxies and looked out, you'd see space. You'd see that everything around you, moving away. And actually, you'd see something even more specific than that, which is that the galaxies very close to you wouldn't move very far in the time I take to stretch it. But the galaxies very far from you move further. And how that can be seen is that distant galaxies should be expected to be moving away faster from you than ones close by. So there's this very specific prediction of an expanding universe, which I'm showing here. Let's talk through it, which is if we have along here the distance of a galaxy from the Milky Way and the speed that it appears to be moving away from us, then if the universe is growing, all the galaxies in it should approximately lie along this line, where the nearer galaxy should be moving away from you slower, and the further one should be moving away from you faster. And if the universe is not growing at all, then there should be no pattern. They shouldn't follow a pattern. And so both Lemaitre and then with better data, Edwin Hubble, in the late 1920s, went to look at all these galaxies that they just discovered were actually separate galaxies beyond our own. And they measured how fast they appeared to be moving away from us. And they found that it was in fact true that almost all of the galaxies around us in the sky are in fact moving away from us. And they followed this trend that the ones further away from us are moving away from us faster. Again, that doesn't mean that we are at the middle of the universe with everything moving around us. If you hopped over to another galaxy, you would see the same thing happen. Everywhere you jump to in space, you would see galaxies moving away from you. And so this was big news. This said that the universe is growing, and actually by measuring how fast things are going, you can do something even better. You can work out when, in the past, that growth should have started. And when the growth started, imagine in your heads you can wind back now. When I shrink down my elastic, I can't get it to stop. I can't get it to, let's say I'm out here. If I wind back time in my head, I shrink back down the elastic, it stops there because my elastic has a finite length. But imagine, if you will, that the elastic could keep shrinking down and down and down and down and further until all those spots were on top of each other. That would be what we call the Big Bang, the beginning of time, when everything that's now stretched apart was right back on top of each other. And so actually just by looking at how galaxies are moving away from us, how fast, you could imagine even just doing this with a simple, if you know the speed that something's moving and how far it is away, I'm pretty sure we can all figure out what time it set off from me, right? That's an evaluation that we can do. And so by looking at the galaxies all around us, astronomers could make the first estimates of how old the universe is. Now, Edwin Hubble and Georges Lemaitre both showed that the universe was growing, and they had this pattern, but they actually got the distances wrong by about 8 times wrong. And so they actually estimated an age of the universe that was only 2 billion years. And after that, there was this subsequent kind of years of understanding exactly how to use these pulsating stars in an accurate way. until in 2001, this astronomer, Wendy Friedman, American astronomer, led a team that used the Hubble Space Telescope to measure these pulsating stars even better and managed to get a really good estimate of how fast the universe is growing. And it was her team's measurement that gave us one of our best current day estimates of the age of the universe, which is about 14 billion years. There's another way you can do it too, which is actually what I do, which is I look at distant light from the Big Bang itself, and we can use that to infer the age of the universe in a slightly different way. And it gives us even a slightly more precise measurement. But the measurements agree broadly. And they point to this time in the deep past, the Big Bang, when everything started. So when we look around, so this big picture of our story is that the universe is growing, galaxies are moving apart from each other, that there was a beginning, some Big Bang. Something quite strange is happening now, that 20 years ago, we went out to measure. We thought, right, the universe is growing. There's some initial energy set off this initial expansion. But, the stuff throughout space filling it, and the gravity of all the galaxies still in space should tend to slow down the growth of space, and should eventually either just slow it down, getting slower and slower forever, or maybe slow down enough to turn around, to stop the expansion, and to reverse and start shrinking again. And this was genuinely an interesting question 20 years ago. It's still interesting, but it seems to be no longer the right question. Because astronomers went to measure very distant galaxies and looked at how fast they were moving away from us. And they did this clever trick of comparing how fast the universe is growing in the past to how fast it's growing now. And they thought they'd see that it was growing faster in the past and not as fast now, slowing down. But they saw the exact reverse. They saw that the universe is growing faster today than it was in the past. It's speeding up. The galaxies are flying apart from each other faster and faster. And this is as strange as if I threw a ball in the air, and instead of coming back down, or in the most crazy example, I throw it so hard that it just kind of coasts off up into space slowly. Unlikely. Instead, this is as weird as if I threw the ball in the air and it sped up away from my hand, away from the gravity's pull of the Earth. And again, this is, along with dark matter, it's one of our big mysteries right now in astronomy and in cosmology, which is that there appears to be something in the universe that is making the whole of space grow faster and faster. And again, we don't know what it is. We call it dark energy, and that really means we don't know what it is. It might be the energy of empty space itself. It might be that as space grows and grows, that every box of empty space has its own energy. And that as space gets bigger and bigger, this becomes sort of more dominant, and it can make space expand faster and faster. But it could be something else. This is, again, one of the big things we want to find out. Now, just as I finish, I just want to, I've had time to talk about the big story. There's also our local story, which is, our sun has not been around forever. And we think that it was born about 5 billion years ago in a place a bit like this, not this place. This is the Eagle Nebula, this beautiful image of a stellar nursery, the place where stars are born. And so within the galaxies that I talked about, these galaxies have these spiraling disks of stars, but they also have these clouds of gas and debris from older stars. And this is an example of them, these beautiful clouds of dust and gas. And inside those are where new stars are forming, where balls of gas are condensing into new stars and drawing around debris disks of kind of rocks and other things that will eventually form into planets. And so we think that our sun itself was born about 5 billion years ago with some planets that coalesced around it. And it was born from the remnants of older stars. Older stars are where our ingredients were created. Everything we're made of was created in the core of a star. Not everything. The only thing that's not created in the core of a star is hydrogen and helium. At the beginning of the universe, that's all there was, nothing else. And so everything, all the oxygen, nitrogen, carbon, everything that's in our bodies was made in the furnace of older stars that then exploded and sent out their material out into space, into some of these stellar nurseries where new stars were born with planets around them that were made of the kind of things we're made of. So we really are made of stars. And I have to skip past these. and so there's this story of, there's the cycle of the stars that create us, and there's the bigger story of how the whole of the universe is growing. And so, we've really found out so much and so quickly about our magnificent universe that's happened really in the last decades. Our knowledge has advanced so much. But there are still tons of fascinating and interesting questions. And what is true is that today's astronomers, and I, won't get to answer them all. But happily someone else will. Maybe some people in this room. Thanks.